Hello everybody, and welcome to your video on writing equations of exponential functions. So just to make sure you're on track here, for day one of this week, you have a discovery worksheet where you're just going to complete it. You don't need any video or any extra help to do it. And then after that, you have these two videos that will show you how to graph exponential functions by hand. You'll upload your work. For day two, which this video is going to help you with, you'll complete this using day one's videos, and then you're going to use the information given here, a1 plus r to the t and a1 minus r to the t. You're going to need those equations in order to do this half sheet right here. So I'm going to take these, and exponential functions have a lot of applications, and unfortunately you're not able to do any of them in class, in your groups, and with me, but I'm just going to tell you what they are. We are going to need to know that A is the initial amount, which it says here. R is the percent increase, or down here if it's decay, R is the percent decrease as a decimal. That's very important. And 1 plus R is the growth factor, 1 minus R is the decay factor. So those are things we'll need to know. Now notice this equation is based on the general form A times B to the X. B is just replaced with either 1 plus R or 1 minus R. Applications that we would have done are the fact that anything related to money, which you're all going to be working with money at some point, whether you work in the stock funds or you're just dealing with your own money, exponential functions are how that works. So there's a lot of applications there, whether you do stocks, bonds, Roth IRAs, mutual funds, etc. So anything having to do with money, they're percents, but they're based on exponential growth and decay. Hopefully, if it's your own money, it's growth, not decay. Depreciation of a car. Cars depreciate based on an exponential model as well. They lose a lot of value at first and not so much value as time goes on. Another really good application is, well, I guess it's not really good one, it's kind of a depressing one, but estimating time of death. Chemistry people, you might have heard of Newton's law of cooling. That's based on an exponential model as well. You have steep decay at first, which then levels off. And that's how forensic scientists go to a crime scene and can determine or estimate whenever someone died. So those are all things that you can explore with exponential functions, but we are most interested in making sure that you can complete the half sheet, writing equations based on a little scenario. So let's remind ourselves here that growth is a 1 plus r to the t, and decay, y equals a 1 minus r to the t. Remember, r is a decimal. If you put a percent in, you're going to get very strange numbers. A is your initial amount. That's the same. This is your growth factor. This is your decay factor. So now that we have that said, we can answer these questions here. This is what the half sheet's going to be based on. They're always going to give you an initial amount and a starting year. And they're going to tell you whether it's increasing or decreasing. So here I'm increasing and looking at my growth. And they're going to tell you the rate. Usually is a percent that it's growing at. And we want to write a formula for the population as a function of the number of years since 2003. So we have to give the value of r. Now r, again, remember, is a decimal. So r is either the percent increase or percent decrease. In this case, it's the percent increase, and 14.5% as a decimal is 0.145. So that is your value of r. Now the growth or decay factor, in this case, it's growth factor b. This is replacing b. I'm going to do 1 plus r. So 1 plus 0.145. So 1.145. And then your equation, you're just going to do a times 1 plus r to the t. So it would be 175. And then 1 plus r, I already did that work right here, 1.145 to the t. Now, remember, this is a times b to the x. Since b is greater than 1, we know we have growth. So our population of turtles is increasing. And another thing to realize is, let's say they want to know what the population now is in 2020 based on this model, assuming the model still applies in 2020, you would not do this. That would be the population of turtles in the year 4023, which you can't even really comprehend that far ahead in time. So you have to notice that T is the number of years since 2003, and 2020 is 17 years since 2003. So that is what you would plug into your calculator. So just be aware that you're inputting the right thing based on when time starts. Okay, next one, an item is currently worth $4.35. So that sounds like my A value, my initial starting value. Now, every year it only retains 82.5% of the previous year's value. So this sounds like the value is going down. So the item was worth this much, it's losing value every single year. So it's not losing the same amount every year. Write a formula for the value of the quantity as a function of time. Here I don't give you a starting year for when time starts. That's okay though. So my value of R. Now you have to be really careful here. This is the percent decrease. I am not going to put 0.825 here because I'm not losing 82.5% every year. I'm retaining 82.5% every year. If I'm retaining 82.5% every year, that means I'm losing 17.5% of the value every single year. So that means my value of R is 0.175. My growth or decay, in this case, decay factor B is 1 minus R, which is 1 minus 0.175, which is the 0.825 that the problem stated. So the way you can think about B in decay is it is the amount retained. So you're losing 17.5% of value every year, but you're retaining 82.5% of value. So my equation will be A 1 minus R to the T, which is 435. 1 minus 0.175 is 0.825 to the T. Now, one thing that you need to realize is to understand how powerful exponential growth and decay are. So exponential growth is the most powerful growth out there. It increases faster than any other function. You start to increase very slowly, but if you're patient enough, it grows quicker and quicker and quicker and basically skyrockets. Exponential decay, on the other hand, you have a lot of decrease at first and then it levels off over time. So in this case, I'm going from $435. Now you need to be able to calculate how you get from 1 year to the next. You take your initial value times 0.825 to get after 1 year. You only have $358. You've lost like $80 there in 1 year. To get after 2 years, you don't take the initial amount, you take the previous year's amount times 0.825. Now you're down to $314, you've lost about 40 bucks. Then you take the previous year amount times 0.825, etc. And what that looks like is, so I'm going to take my function and I'm going to graph it. You have a ton of decrease at first, it eventually levels off at the horizontal asymptote that every exponential function has. And if I go to the table here, my values are what I got before. So eventually you're only going to be losing less than 20 from one x to the next, as opposed to about 80. And you can really see the leveling off. You're hardly losing anything eventually. That's all for the video. Good luck on the worksheet. Email me if you have any questions. Bye.